Welcome pre-K and kindergarten students to the Dallas Independent School District STEM Environmental Education Center. We'd like to give a special welcome to students from Withers Elementary and a special welcome to the girls at the Solar Preparatory School for Girls. Thank you so much for registering for this field trip. If you are watching this and you have not registered for this field trip yet, you can still get yourself or your class registered by going to www.tiny.cc/EEC register to get yourself registered for this field trip. We just use that information for our attendance purposes. Today's field trip is going to investigate heating and cooling. During this virtual field trip, students will observe and discuss how materials can be changed by heating or cooling. So you are going to see something called evaporative cooling. We're going to look at what happens in the sun versus what happens in the shade. We're going to do some cooking with a solar oven and conduct a bouncy ball investigation. And while we do all of that, you can ask us questions, but since this is a virtual field trip, you're going to need to go to this website to do that. And that is www.tiny.cc/EEC-question-answer. And you can ask us any question you have related to heating or cooling. And you can ask us as many questions as you like, and we will do our best to answer them this afternoon. So I'm going to stop sharing my screen here and turn it over to Mr. Monroe, who's going to get us started with evaporative cooling.
All right, students. My name is Mr. Monroe, and I'd like to welcome you on this virtual field trip that you're participating in with me today, the other teachers here. And my part of the program, or of your field trip, we're going to do a very special study on a process called evaporative cooling, okay? And actually, it's how when we perspire or we sweat, it's keeping our body cool. We're going to study that process, how it works, and then examine why that process, which we call evaporative cooling, is important to life on our planet, the planet Earth. Let's take into consideration, you're playing out in the yard at your house, maybe last year during recess, sometime when it was very warm or very hot, and you began to sweat and perspire. Well, it's time for you to go inside. Once you go inside, you sit down and you're still, and then all of a sudden your body gets cool. Well, guess what that was? That was evaporative cooling. It's how sweat can cool our bodies down when we get close to overheating. And to really get a basic understanding of that process, evaporative cooling, we're going to look at some processes that happen with that wonderful substance that we call water. You know, water is constantly recycled. You guys will learn about the water cycle as you get a little older, but there are certain things that happen to water. First of all, this word right here, evaporation. Now, that is water changing, or the liquid form of water changing into the gas form. Once it's in the gas form, then it's very light and it just goes everywhere. We call the gas form water vapor. And it enters the air and the atmosphere, and then it goes through some other processes. This is the one that we're going to kind of focus on today because the process is called evaporative cooling, okay? Now, we know that water can hold heat. It can hold heat without actually changing how hot or cold the water is. It stores that heat in it. And then once it goes through the process of evaporation, changing into the gas form, guess what? That gas form, that water vapor, takes the heat with it. You know, I've got a little experiment that you can even try, maybe at home or even at school there. But if you had a container, maybe a cup, and this is nothing but water in this beaker, dip your finger in it, raise the finger up, and blow on it, you will feel just a little cooling sensation from the air blowing across your wet finger. And you know what? That's an example of evaporative cooling. Now, the heat that water is storing or is holding on to, it has a different name of heat. It is actually called latent heat. Now, once that heat is stored and absorbed by the water, again, when that water changes into the gas form, it takes the heat with it. If your hand was wet, your arm was wet with sweat, and a little bit of breeze came across that to accelerate or speed the process of evaporation up, it wouldn't be long before your skin would cool down. Evaporative cooling. Now, listen, students. When I was very young, growing up where I grew up in the country, my great-grandmother, we didn't have an air conditioner. And from time to time, I would see my great-grandmother go outside, and we had these two big units that were in the windows at our house. They weren't air conditioners either. They were something that we call water coolers. And I would watch my great-grandmother as she would take the water hose and she'd go behind those big old units. Part of them would be sticking in the window, and she'd shoot water into the back of that unit. And one day I was standing there real close watching her, and I could see that in the backside of those units, where there was pads and some filter-like material, she was squirting that water from the hose on those filters, soaking them down with water. And then she'd turn the water off, and we'd go back inside, and she'd turn the fan on, which was inside that unit. Man, that air coming out of that unit was so cool and refreshing. I couldn't figure out how that worked. But guess what? That was evaporative cooling. Because what was happening in there, hey, the water was evaporating. It was taking the heat away from the air that was blowing through there. And guess what? It cooled the air. You know what? Even today, they sell water coolers. You know, I bought one about a year ago, and it was very small. It was a personal unit called Arctic Air, and all it is a water cooler. I have two of those units right here in front of me, and we're going to run a little experiment to see if evaporative cooling is going to occur in one of these. Now, the first one I've hooked up, it doesn't have any water in it. And in a few minutes, I'm going to start it. In a minute or so, I'm going to start it. And I'm going to use a scientific tool that we use to measure how hot or how cold something is. I think you guys probably know what I'm talking about. It is called a thermometer, okay? And we're going to take the temperature of this unit first that doesn't have water flowing through the filters and the pads in the back, and see what that temperature. Now, these are made just like the water coolers were made long ago. In the back, there are some pads and filters in here. There's also a fan that's going to pull air through. And the air is going to vent out the front to cool whatever's in front of it, to cool it off, okay? And again, we're going to use a thermometer to take the temperature. If you look at this thermometer, you will see a red fluid in it. Now that red fluid is going to act on the air temperature coming out of these units. If it's warming up, you'll see that red fluid go up. If it's cooling down, it will go down and probably stay low. But you know, I don't have much time with you. It would take a little too long for the fluid to move. So I'm going to use a different type of thermometer. It's called a digital thermometer. And it has a probe on it that has a sensor that is going to read the temperature real quick. And it will send the results to the little monitor, and we'll be able to read that temperature real quick. So I'm going to go ahead and start this one. I hear it blowing. The air is blowing. I'll give it just a minute. I'm going to turn my digital thermometer on. I'm going to put the probe in front of the air. Now I'm going to take a reading in Fahrenheit and Celsius. Fahrenheit would be the customary measurement. Celsius would be the kind of like the metric. All right, now, I know you guys probably won't be able to see this, but right now the air coming through this vent is about 72 degrees, 0.7 degrees Fahrenheit. Okay? That's the one without water. Now, if we were using a thermometer like the one I showed you earlier, you would see the red fluid. So if this was a real thermometer, it would probably register right up there. That's 72 degrees, okay? Somewhere right in there. Okay, now, this is the one that we're going to put water in. Now, I haven't put the water in it yet, but it has a reservoir with a door. And I'm going to pour water into that door, and it's going to soak down those pads that are in the back here, and we're going to start the fan, and we'll see what happens then, okay? We'll see if there's going to be a temperature difference. Now, the container that I have here, oh, it's just like a jar, a bottle that you would use. It is glass, but in the science world, this is called a flask. All right, I'm pouring the water from the flask into the reservoir. Okay, I'm going to give it a little time to drain to the back and go down the pads. Clear that thermometer, and now I'm going to start the fan. There it goes. Wow, that air feels like it's a lot cooler than this. We're going to see here in just a minute. Okay, I'm going to put the probe up there, and we'll see what happens. I can see the temperature's dropping already. I don't know whether you guys can see that or not. It's down to 66.9 degrees Fahrenheit. Yes, it is dropping. It's 65, 64. It's going on down at 63. So indeed, evaporative cooling is going on with this unit here. So, wasn't any water here, no evaporation going on, but this one had water, evaporation was going on, so we did have evaporative cooling in this unit. So hopefully you guys have seen how that works. It's very important because, you know what? Of course, we have our own built-in system. We perspire and we sweat when we get pretty warm or get close to being overheated. And that's our way of our body cooling us down so we don't get overheated. So sweating and perspiring is a natural process for us. But there are some living things in our world today, guess what? They cannot do that. We have a couple of big hogs out at the barn. And you know what, guys? Sometimes I feel so bad for them. People just don't realize that hogs and pigs, they cannot sweat. They cannot perspire. You know, if you were here today or maybe on a hot day and we walked out to the barn so you could see Shotzi and Gracie, you probably would think, ooh, they're nasty. Because you might see them wallowing in a big old puddle of mud and water. And you probably wonder, well, what are they doing that for? Getting themselves all messed up. Well, guess what? What they're trying to do is keep their bodies cool. Simply because they cannot sweat. They cannot perspire to cool their body down. So they have to find a place where there's water or maybe even mud to roll over in to cool themselves down. And I can remember one story. I got into trouble one time because we had a few pigs and I was out there just playing with them, chasing them on a hot day. And again, my great-grandmother, who was probably one of the best teachers in my life, she came out and she said, little boy, leave those hogs and pigs alone. If you keep running them in this heat, you're going to make them sick and they might die. Now I understand what she was talking about. So hopefully you guys have got a little understanding about evaporative cooling and how it works, keeping us cool as far as sweat and perspiration, and even with the units that were used long ago called water coolers. So hopefully I've answered some of your questions. You got a better understanding of that term or that process. But if you don't, I'm going to let Mr. Barton take it back over because he may be able to answer some of those questions that you might have. All right, Mr. Barton.
Thank you, Mr. Monroe. And the question that came in was, do any other animals use evaporative cooling to cool themselves? And the answer is yes. One example that I'm sure you've seen before is a dog. When a dog pants, that is a form of evaporative cooling because dogs cannot sweat just like pigs. And an example that maybe you haven't heard of before is a kangaroo. There are kangaroos that live in the desert of Australia. And what they do is they lick their arms a whole bunch of times and get their arms kind of all wet with their saliva or spit. And when that evaporates off their arms, that helps cool their body. So I'm actually glad that I can sweat because it would be gross to have to lick yourself to get yourself cooled down. All right, now we're going to move on to what happens in the sun versus what happens in the shade with Miss Nash.
Yes. Where am I? Please come in. Oh, there I am. Okay. Hello, welcome to my classroom. And today we're talking about sun and shade. And I wonder what you like best. Do you like the sun or do you like the shade? Maybe it depends on what time of year we're talking about, right? So in the summertime, the hot summer, we're looking for that bit of shade all the time, looking for it. But right now, it's kind of cool today. I was out in the garden earlier and the sun felt really good. So sometimes it depends on the season, whether we like the sun or the shade. Now, we can also, if we're too hot, we can bring our own shade with us, okay? Wear a hat. We can bring a little evaporative cooling with us, keep cool. We can also choose what color clothes we wear. So I have two t-shirts here, a black one and a white one. And the black one feels really hot, that little sun lamp there. The white one, not so much. So if you're gonna be out in the sun, white is a good color if you don't want to get too hot. So we can make all those kinds of choices, right? But animals and plants, well, not so much. So plants in particular can't walk around. They can't really move. So some plants, like this little succulent here, a plant kind of like our cactus, okay? And these guys really like the sun. Okay? So they don't like to live in the shade. They want sunshine, and they don't mind how hot and dry it is. But other plants, like my little fern friends here, they would die in that sun. They got these little thin leaves and they would just wither and dry up. They like to live in the shade. So some kinds of plants live in the sun and some kinds like to live in the shade. Animals are the same way. Some animals don't like that sun. So I've got my friend here, cockroach number 45. And this one is a big cockroach, not the one from my kitchen. But the ones in my kitchen, when I come in at night and I turn that light on, they're running for cover. Because they think, uh-oh, the sun's out, we better run away. We're animals of the darkness, the shadows. So these guys like to hide in a shady place, hidden away. Another animal that doesn't like the sun, my froggy friend. See my little leopard frog? See those spots on him? Isn't that cool? He's called a leopard frog. And look at those big eyes. He can look around for bugs and find them and catch them with that tongue. But he does not like to sit out in the sun because he dries out really badly. So he's going to be hiding in a shady, cool spot or in the water. Okay. So froggies don't like the sun very much. But other animal friends really need the sun. So my friend here, this turtle, and this is a common local turtle. You'll see them all over town in any park. There's a lake or a stream, you'll see them. Have you seen them? Look at those webbed feet. He can swim pretty well with those feet. So this is called the red-eared slider. And you see the red mark. Oh, you can bite me. The side of the head. And if you get, they're sitting on that log in the sun. They're basking. And they're using that heat from the sun to get get warm. That's the only way they can get warm is from the sun, okay, to bask in the sun. Because this is a reptile, a cold-blooded animal. We call it cold-blooded, but really their body temperature changes. So if you feel your neck, you're always warm. But these guys, sometimes they're warm and sometimes they're cold, depending on where they are. So they need to be warm, pretty warm to be active. Okay? So they have to bask in the sun to get warm. If you get too close to that log, they will slide away and escape into the water. Another one that you might see at the side of the pond is a little snake basking. So another reptile. So again, they have to get warm by sitting in the sun. And when it gets really cold, then they have to hibernate. Okay? So in the spring and the fall or early in the morning in the summer, they'll be out basking to warm up so they can be active and go hunt for tadpoles and little fish. The garter snake or ribbon snake. Now, here's another reptile that's not so crazy about the sun. So this one, this is gecko, and this little gecko comes from a desert in Africa, North Africa, and it's really, really hot. So too hot for them. So they can get too cold and they can also get too hot. So he's going to be in the shade, under a rock in the shade, waiting for the sun to start going down before he goes out to hunt for bugs. Look at those giant eyes. Okay. So he's going to kind of try to avoid the sun. See that fat tail? And so he can make it through the tough times ahead. Go over. So now all the animals use sun and shade as a way to survive, and so do plants. And what I'd like you to do now is go around, take a piece of paper, fold it in half, and then on one side, I want you to write sun and shade or sol y sombra, and go around and see if you can find plants and animals. Some live in the sun and some in the shade. Sol y sombra. And then draw me a picture of the animals that you found and the plants you found living in those two different places. Thank you. And if you have any questions, Mr. Broughton would be glad to answer.
Thank you, Miss Nash. And I took a little trip out to the barn here. So if I kind of pan around, you can see that I'm inside of our Environmental Education Center barn. I'm going to flip my camera here so you can see those pigs that Mr. Monroe was talking about. So this one's name is Gracie. She's a Berkshire pig, and you can see that she's got quite a bit of mud on her. Let me get a good look at her. Give you a look at her face here too. There she is. And look at all that mud on the side of her. That helps keep her cool, especially when it's wet and it evaporates off of her. That's how pigs can use evaporative cooling to stay cool. And it acts like a sunscreen too to keep the sun off of them because they can get sunburnt actually. And then this one over here is Shotzi. She's another Berkshire pig. And just to give you an idea of how big these pigs are, I'm going to give her a little scratch behind the ear. And you can see her ear is bigger than my hand. They are big, 600-pound pigs that like to stay cool in the summer using mud. So there's our pigs. Now we're going to move on to solar oven cooking with Mrs. Fuller.
Hello, students. My name is Mrs. Fuller. We're talking about heating and cooling today. So I'm at the second section of the program where we talk about using heat from the sun. I'm sure you've seen people make s'mores on television. Maybe if you've been camping, you've made them also. Well, they're very delicious. It's a fun thing to make, but did you know you don't have to have a campfire in order to make s'mores or a stove or an oven? You can actually make them with heat from the sun. This is a solar oven. I'm going to hold it up so you can see it. It's called a Sunspot. This is the kind that we use here at the Environmental Center. It uses a heat from the sun both from direct rays that come from the sky and go directly in, but also from reflective energy from the rays of the sun that catch the sides here. It looks like aluminum foil, and it gets directed into the solar oven. Let me pull the bottom off, and I'll show you what it looks like inside. It looks just like a box, because that's what it is. And it's got a black construction paper. Now remember when Ms. Nash told you about black t-shirts absorb energy from the sun and white t-shirts reflect energy from the sun? Well, this is a case where you want some black construction paper to absorb that heat energy and heat the oven up. Now, when you look down where the rays from the sun come in, there's a, can you hear that? That's a plastic lid. There's a little bitty tiny hole in the middle where my finger is that lets any steam out if there's any steam. And that keeps the heat from escaping. So I'm going to show you how to make s'mores using a solar oven. So you take a square of graham cracker and you put it just right there on the floor of the oven. And you take a piece of milk chocolate and you put it right on top. Then you take a second square of graham cracker and put it down, and put several of the miniature marshmallows. Don't use those great big ones. It takes them too long to get soft. Now these are not going to get all puffed up and turn brown like when you use a campfire. Anything that you cook in the solar oven will not brown. It will not caramelize. But they'll get very, very soft and squishy, and the chocolate will melt all the way. And when you press them together, it makes a perfect s'more. Now I've got another solar oven right here, and I already have some in here. So I'm going to show you what they look like. And the little oven is pretty warm. I can put my hand inside of it and feel that warmth from the sun. So here's the melted chocolate. Can you see that? And here's the soft, squishy marshmallows. I'm going to push this one in the center. And then you just push them together like that. Can you see that chocolate oozing out the side there? Doesn't that look delicious? Yeah, well, that makes a really good s'more. But you might say to me, well, Mrs. Fuller, that's all well and good, but you can't live on dessert, and that's true. Well, here's the soup that I'm going to eat tomorrow for my lunch, and I can pop the top off of it and get a casserole dish and pour my soup inside and put a lid on it to keep the heat trapped inside the casserole. Put it inside the solar oven, put it in the bright sun, and when it's time for lunch, my soup will be hot and delicious. Just about anything you can cook in a slow cooker, in a crock pot, you can cook in the solar oven. And it'll get real toasty warm, and it will cook your food so for your lunch or for your dinner. Now, there are some great advantages to solar ovens. There are people all over the world that do not have electrification, that don't have electricity in their houses, and they have to go gather sticks and wood during the course of the day so they have enough wood to cook their supper for their family. Well, this eliminates all that time they would be out looking for wood by letting them cook it in the solar oven. So they just would put their dinner down here in the bottom part and put this out in the sun. And when it was time for dinner to start, the food would be cooked for them. So that's a big savings of time and energy and money. There are some drawbacks to this particular type of technology. For one thing, if it's raining, it won't work. If it's real cloudy, it won't work. You have to have a nice, bright, sunny day like what we have today. Also, yesterday when I did this demonstration, it was very windy. It was windy all day long. And two or three times my solar ovens blew away and took the food with them. In that case, if I was trying to cook something for my lunch or for my dinner, I would have to stand there and hold the boxes to keep them from blowing away. And that would mean my whole day would be wasted just making sure that the solar oven didn't fly away. So that's also a day where it's probably not a good idea to use the solar oven when it's very, very windy. So you may say to me, well, this is great. I'm glad that the Environmental Center has a bunch of sunspots for the boys and girls to use to make s'mores, but I don't have that at my house. Well, guess what? You can look on the internet and they have really easy instructions to make your own at your house from a pizza box, believe it or not. You will need an adult to help you, but the only ingredients you need essentially are an empty pizza box, no pizza inside, black construction paper, some plastic film. Yeah, you'll have to have an adult cut the window in the lid and tape the plastic film down, and then you have a solar oven too that you can make s'mores at your own house. Now, Mr. Broughton is going to answer any questions you have about solar ovens. I hope you have a delightful afternoon, and I'll see you later. Thank you.
Thank you, Mrs. Fuller. The question that came in is, where can I find directions on how to make my own pizza box solar oven? So I'm going to show you how to do that. The first thing you're going to need to do is find an adult, because you're going to need to go on the internet, and you should not do that without an adult. But once you have your adults, I like to start at google.com, and I'm going to type in pizza box solar oven and hit enter. And there comes up 3 videos about how to turn a pizza box into a solar oven. And there's some websites as well. I'm going to just choose this first one as an example. It's from Scientific American, and the title is Sunny Science, Build a Pizza Box Solar Oven. And it lists the key concepts that you will learn as you build your solar oven. There's an introduction and background to help you get started. It tells you all the materials that you're going to need to build your solar oven. Although you can see here it says have adult help, so make sure you have an adult help you with that. And then the preparation and procedure tells you step by step how to make your solar oven. And once you're done with that, you'll be cooking in no time. So that is how you can find directions for a solar oven. Now we're going to move on to the bouncy ball investigation with Mr. Ramirez.
Hello, my name is Ms. Ramirez, and in this segment, we're going to be learning about how temperature can change materials. So hopefully you remember from Mr. Monroe's segment that we use a thermometer to measure the temperature or the amount of heat energy that a material has. So when we talk about temperature, we're talking about the amount of heat energy. So what are some ways that we can add heat to materials to make them hotter? Also think about what are ways that we can remove heat to make them cooler or cold. So be thinking about different ways that you might use at home or at school to add or remove heat. I'm going to show you a few examples, and y'all are probably already familiar with some of these. If we wanted to add heat or make things hotter, you could use an oven or a stove, a microwave, maybe a campfire, or as Mrs. Fuller showed you guys, we can use the sun's energy to help us heat things up. Now, what if we wanted to do the opposite? What if we wanted to remove heat and make things cooler? Well, we could put things in a cold refrigerator or freezer. If we wanted to make our drink cooler, we could add ice. But also our air temperature changes during the season. So during the winter time, we have a cooler air temperature. We might see snow or ice, while during the summertime, we have a hotter air temperature. So let's look at an example of how temperature changes materials. And we're gonna first look at our popsicles. So y'all are probably familiar with popsicles. These are kind of like the ones I grew up eating. Make some observations. What do you see? What do you guys notice? compare these two. So how are they different? And what do you think happened to them to make them different? So let's start with this one. Because I'm able to actually touch them, I can feel that this one is squishy. So I can squish it and you can see it's a liquid. So the liquid is moving. You can see it flowing through the plastic wrapper. It also feels warm to the touch. This one, on the other hand, is different. This one feels hard. I can't squeeze it. It is also really cold because I just took it out of the freezer. It's a solid, so it doesn't move freely throughout the little plastic container. So this one is a liquid and this one is a solid. So how I got a solid, I simply put this in the freezer. I removed heat energy. It got really cold and it froze and turned to a solid. Now, if I had this solid popsicle, what is something I could do to make it turn back into a liquid? Well, super easy. You can either leave it in your room and let it start to melt as it gets warmer, or if you wanted it to melt faster, you could stick it outside on a hot summer day, and then the sun's heat energy would start to melt the solid popsicle and you would get your liquid back again. So do you think all materials will behave the same way? So do you think all materials will melt when they get heated? Do you think all materials will turn into a solid when they get cold? So we're going to look at an example of how other materials might change. So we're going to be doing an experiment with a bouncy ball. We have heated up 3 balls. So one bouncy ball I left at room temperature. One bouncy ball I put on a hot plate, and a hot plate is kind of like a little mini stove top. I put water on a hot plate. I got it really hot and to boiling, and then I put my bouncy ball in that hot water. And then I have a cold bouncy ball that I stuck in the freezer overnight. So we're going to test to see what happens to these different bouncy balls at different temperatures, and we're going to see if it affects their bounce height. So before we do our experiment, make a prediction or a guess. What bouncy ball do you think will bounce the highest and why? Now, I'm going to show you a video of the experiment because I couldn't do it now because I have to have that bouncy ball super cold, and you have to do the experiment right after you take that bouncy ball out of the freezer. So I tried doing it live yesterday and the results did not come out like they were supposed to, because by the time it was my turn to present, my bouncy ball that was frozen had already gotten quite warm, almost to room temperature. So if you do this experiment at home with the help of an adult, just make sure that you do your bouncy ball that's frozen, make sure you drop it first. So I'm going to go ahead and share my screen, and I'm going to show you guys the video. Y'all are going to practice being a good observant scientist. Y'all are going to use your sense of sight and also sound. Notice some of the sounds the bouncy balls make as you guys observe the experiment.
Today we're going to be doing an experimental investigation to see which ball will bounce the highest. We're going to compare a ball that was set at room temperature. We're going to compare a ball that's been placed in hot water and a ball that's been placed in the freezer. So let's look at some of our science equipment that we will be using. Here we have a hot plate. A hot plate is kind of like a little mini stove top. It is heating the water inside this beaker and also the ball, which is floating in the beaker. So a hot plate, the temperature right now in that water is about 90 degrees Celsius or 194 degrees Fahrenheit. So that's going to be our hot bounce ball. Then we have our cold bounce ball here in the middle. It was in the freezer. It was about -10 degrees Celsius or 14 degrees Fahrenheit in the freezer. I placed it in a beaker full of ice just to help it stay a little bit colder. And then we have our room temperature ball, which is about 22 degrees Celsius or 72 degrees Fahrenheit is about the temperature in my room. Now we're going to be using a data chart like this to record our data. We're only going to have time to do one test today, but ideally a scientist would conduct at least 3 or 4 tests to make sure their results are accurate. But we will be filling out our chart. And then we also have this height chart just to make it a little bit easier to see how high the balls actually bounced. And I just used the meter stick that you see above us to help us mark some lines. I used it in inches and in centimeters. We're going to test the cold ball first. That way it doesn't have time to warm up in my room. We're going to drop it at a height of 43 inches. So hopefully you saw that it went just above 20 inches, and I hope you heard that loud sound it made when it smacked the floor. So we're gonna put our mark for 20 inches for the cold ball. Now we did our cold ball, and that was just above 20 inches for its height. So now we're gonna do the room temperature ball, and we're gonna drop it at the same height, about 43 inches. So you can see it went around 35 inches, so we'll go ahead and mark that. And the last ball that we're gonna test is the ball that's been heated using the hot plate. So I'm gonna use a spoon to take that out of the hot plate in the hot water, and then we'll drop it again at the same height. And it went just above the room temperature ball. So you can see that the ball that bounced the lowest was the cold ball. The room temperature ball and the hot ball actually bounced the highest. So we're going to discuss those results in just a little bit, but we're also going to take time to put our results into our little data chart as well.
Okay, I'm gonna stop sharing the screen and then we'll talk about our results. So hopefully you guys were able to see that the ball that did not bounce very high was actually the cold ball. And I conducted this test 4 times, and overall, the hot and room temperature balls had the highest bounce height, while the cold bouncy ball always had the lowest one. Hopefully you guys were able to notice the difference in sounds that the different bouncy balls were making. There was a big difference between the way the cold ball sounded when it hit the ground versus how the other 2 bouncy balls sounded. So the cold bouncy ball, when I took it out of the freezer, you could feel a difference in how it felt. It felt literally like rock hard. It was really hard and solid compared to the way these other 2 bouncy balls felt. So it was no surprise to me that it made that loud noise when it hit the ground. So why exactly was that cold ball not able to bounce? Well, it all has to do with particles. All matter is made out of small little particles. So what ends up happening is with temperature, the particles either slow down or they move really fast. So in the case of our cold bouncy ball, the particles that are inside the cold bouncy ball, when I put it in the freezer, those particles they froze. They got really slow moving, and there's not a lot of energy in it. So when I dropped it, it didn't have a lot of energy to bounce back up. Now, it also affected its elasticity, and that's this word here. Elasticity is just the ability of a material to go back to its original shape. And y'all are probably familiar with elasticity because you've probably seen a rubber band, or I put a band on my hair. So the rubber band, I can stretch it, but it always goes back to its original shape. It's the same thing with the bouncy ball. When you drop the bouncy ball, it gets slightly compressed when it hits the ground, but then it regains its shape and it uses that energy to go back up and bounce. So you want a bouncy ball that has good elasticity, otherwise it's not gonna bounce. So if you compare it to a marble definitely feels different than a rubber bouncy ball. The marble feels much more solid, very hard, and it doesn't have very good elasticity. And then when you compare our cold bouncy ball particles to our room temperature bouncy ball and our hot bouncy ball, the particles that are within these bouncy balls, they were moving much faster, they had more energy, and they were able to bounce higher. So that's our bouncy ball experiment, and it just shows us that materials react differently to heating or cooling. So not everything's gonna melt just because it gets heated up. So the last thing I wanted to show you guys is just a little video. It's gonna be some ducks that are out here on our farm, and it's a challenge question. So I want you to be thinking about how does the heating of water and the cooling of water affect our farm animals? So I'm gonna share my screen again. I have a super quick video to show you guys. Again, be observing what you see. So hopefully you were able to hear those sounds from not only the ducks, but the chickens and roosters that were out there as well. I'm gonna stop sharing my screen and we're gonna finish our presentation off. So again, be thinking about what's going to happen to that puddle of water during the wintertime when it gets cold. What's going to happen to that puddle of water during the summertime when it gets super hot? And how is that going to affect our farm animals out here? And that's all I have for you guys today for heating and cooling. We're going to pass it back to Mr. Broughton, and he's going to answer any questions that y'all might have.
Thank you, Mr. Ramirez. We're going to do a quick recap of what we covered this afternoon. So this afternoon, we investigated heating and cooling, and during this virtual field trip, students observed and discussed how materials can be changed by heating or cooling. So Mr. Monroe showed us evaporative cooling. Ms. Nash showed us what happens in the sun versus what happens in the shade with animals. Mrs. Fuller did some cooking with a solar oven. And of course, we just saw Ms. Ramirez conduct that bouncy ball investigation. Thank you so much for joining us this afternoon. Please let us know what you thought about this field trip, and you can do that by going to www.tiny.cc/EEC feedback to fill out a short form to give us feedback on what you thought about today's field trip. We do value your opinion and use that to help improve what we do here at our center. And so I'm going to say goodbye and wish you a great rest of your day. Bye-bye.